Good morning, folks. Well, good whenever. I keep forgetting that you can just watch these whenever you feel like watching them. But so good whenever. Hello. In this video, we're going to be talking about implicit differentiation. So what implicit is, essentially implicit is just a way of messing with things, messing with even non-functions, without having to solve for y to make it a function. So here, just to kind of help you see the difference, God, I keep hitting that button, man. To see the difference, right? Come on, pencil. Ay-ya. Come on, technology. Killing me. But the implicit form, as you can see right here, right? This is the implicit form where I'm not necessarily solved for y. This is explicit where I am solved for y, and then I can find the derivative, right? So this form, from the explicit to the derivative, you should be pretty comfortable in doing to this point, right? That's what we've been doing all along, is solving for y. Well, we haven't been solving for y, but having it y equals or f of x equals or whatever, and then doing the derivative. So now what we can do is something called implicit differentiation. And this is where using the chain rule is really, really important. But let's say I want to take the derivative of this thing. So the derivative of xy equals 1 with respect to x. So this first part, it's important to note, is a product rule because we have x and we have a function of y, whatever that is. So if I do this as a uv prime, right, where I have u and v, so the derivative of x is 1 times the second plus the first times the derivative of the second, which I don't know what that is, especially when it is with respect to x. The derivative of 1 equals 0, so I'm left with this. Now, if I were to subtract the y, then x times dy dx equals negative y, and I divide by my x, so dy dx equals negative y over x. That is an implicit derivative, where it's in terms of y and in terms of x. I can make this all be in terms of x if I want to, right? I can take the fact that y equals 1 over x and substitute it back in, because really, this is negative y, so negative 1 over x divided by x, which would come out as negative 1 over x squared, which, hey, imagine that, is the same thing that I came out with when I did it just from the explicit form. All right, this was saying x to the negative 1, so if I did my power rule, then y prime would be negative x to the negative 2. Same thing. So it's still finding the derivative in a good form. Sometimes we'll have some rewriting to do, but like with this example 1 down here, right, this is not even a function unless I'm graphing it with my x-axis and y-axis kind of flip-flopped. But it makes it so that I don't have to solve for y. I don't have to try to solve this cubic function for y, which would just be not fun at all. So let's get into it. All right, find dy dx, given that y cubed plus y squared minus 5y minus x squared equals negative 4. So the first step for me is going to be take the derivative of the entire equation. So now, the thing to note here is when I'm taking the derivative of this part, right, this is going to use a chain rule because I have some function y inside that cubic function. So the way this is going to work is the derivative with respect to x of y cubed is 3y squared times the derivative of the inside, which would be dy dx, the derivative of y with respect to x. Plus, same thing with this other one, minus 5 times dy dx minus 2x equals 0. So the x's are easy. The x's are still kind of like what we're used to doing when we are integrating in terms of x, right? The derivative of this thing with respect to x. So if I'm taking the derivative of x, then dx would divide and make 1 essentially. So what else do I need to tell you? Nothing I can really think of. I think it's just going to be you getting used to it. Right, it's just going to be a matter of thinking, hey, I'm doing the chain rule every time that I'm taking the derivative of y. Even in this other one, if you think about it, right, the whole thing was 5y to the first, so then you brought down the 1, you did y to the 0, and y to the 0 is just 1. Yep. All right, so now the other thing here is that if I am trying to find dy dx, here is where I do need to solve for dy dx. But what I can do is I can factor it out of this first part here. So dy dx times 3y squared plus 2y minus 5 equals 2x. So I added the 2x to the other side, and then I factored out all these dy dx's. Because now if I'm trying to solve for dy dx, then dy dx is 2x over 3y squared plus 2y minus 5. Right, and it didn't tell me that I had to put it all in terms of x or anything like that, so I'm just going to leave it like that. Dy dx is 2x over 3y squared plus 2y minus 5. That is my implicit derivative. All right, let's do another one. Right, so same sort of idea. I have a couple of product rules here with that x squared y plus y squared x. So I'm getting after it. D over dx of both sides. All right, so this first one, I would have 2xy plus x squared. I'm going to use y prime in this time. Remember, y prime is the derivative of y with respect to x. It just is less writing. So x squared y prime plus y squared times the derivative of x, just 1, and then plus the derivative of y squared, so 2y y prime x equals 0. Okay, so now looking at this, I have a y prime there and I have a y prime there, and the other parts can go to the other side. So I'm going to leave this x squared y prime plus 2y y prime x equals negative 2xy minus y squared. So I move this factor, or that term over, and then the other terms are staying there. Then I can factor y prime. And divide out that term. So y prime, or dy dx, equals negative 2xy minus y squared over x squared plus 2xy. And that's it for that one. All right, let's do another one. Natural log of xy. So this is a, let's see, chain rule mixed with a product rule inside there when I take the inside derivative. So if I'm doing the derivative, I would have 1 over the thing inside with that natural log times the derivative of the thing inside. So that would be y plus xy prime plus 5 equals 0. Don't forget the derivative of a number is 0. Please, please, please remember that. I know I always kind of mess that up, and I'm like, why am I getting this wrong? And then I realized that I took the derivative of 1 and made it 1 or something like that. Okay, but again, this was uv, so I have u prime v plus uv prime. All right, so now I just need to move things around carefully. So I'm going to subtract 5, and then we will need to multiply that xy. So 1 over xy, y plus xy prime equals negative 5. If you multiply the xy here, and then I'll subtract that y, so xy prime equals negative 5xy minus y. Divide by the x, and y prime is all of that. I'm trying to save you guys time in showing that work, so don't show work that sloppy, please. Okay, so now here, right, we're not dealing with a function, but I can still find the slope of the tangent line. This graph Let me pull up Desmos real quick, and I'll show you what it looks like. I have it open yet. Come on. Come on. Whoop, 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 whoop. Da, 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 da. Go, go, go. I'm sorry, I should have done this before. Just skip ahead. Skip ahead, skip ahead, skip ahead, skip ahead. Unless you want to hear me sing. You probably don't, so skip ahead. Okay, so there's my graph. Kind of cray-cray looking, right? And it's weird, I don't even know. I don't know what to call that, right? But what I'm looking for is the tangent line at 2, 2. So I want to find what my tangent line is to that point. Maybe the slope is like 3 or 4 or something. I don't know. Let's find out. I'm going to leave it down there so I can pull it back whenever I want. Okay, find the slope of the tangent line. So I first need to find the derivative, right? Slope of the tangent is still related to the derivative. So dy dx at 2, 2. So different ways to do this. You can solve for y if you want to, but I'm not going to. So let's see. We have uv prime over here on the left-hand side. So I'm going to leave it the same the first time, and then 2y, y prime, and then plus negative 1, y squared, equals the derivative of x cubed, which is 3x squared. So now the nice thing here is you don't necessarily have to solve for the derivative once you get more comfortable with these things. You can put all the numbers in first and then solve for the derivative, but I'm going to show you guys the way of solving for the derivative first, just so you are more comfortable with it. All right, so 4 minus x, 2y, y prime, and then I'm going to add that negative y squared over, so I have 3x squared plus y squared, divide by the 4 minus x, and the 2y. Why not do it all at the same time? All right, so there's our derivative. And the way that you will see this notated sometimes is when we are evaluating at 2, 2, is I'm going to do the derivative at, that's kind of what that bar means, 2, 2, and that is going to be 3 times 2 squared plus 2 squared over 2 times 2, 4 minus 2. So many 2's and so many 4's. So that's 3. 3 times 4 is 12 plus 4 over 4 times 2 is 8. So this would be 2. So I was a little bit off with my slope there, but we were kind of close. All right, so there's my slope of the tangent line. If I wanted to write the equation, right, I would have y minus 2 equals 2 times x minus 2. Not just because this is a 2, but because these are also 2's. Everything is a 2 there. So let's look. Let's see. 2x, 2 times x minus 2 minus 2. Whoa. All right, cool. So we are intersecting 2, 2. That looks like a tangent line if I have ever seen one in my life. Only hitting it at one point, and it is hitting it at a 90-degree angle to my curve. I think that one's probably good there. All righty, let's keep going. All right, so these, we're going to take a little bit more finagling, but these are kind of fun. So implicitly in terms of x and y, so notice it says in terms of x and y, so I don't need to solve for y or anything. You could in this one, but it wants it in terms of x and y. So let's see. Sorry. So finding the first derivative is what we've been doing up to this point. So the derivative with respect to x, right? So the first part here would be a product rule. So 2xy plus x squared y prime minus 4 equals 0. And then I have to take the second derivative. But to take the derivative of a derivative, here, let me dy dx. I'm going to leave it as this in this case. Right, and that's the derivative of that function y. So what I would like to do is go ahead and solve for dy dx first. So let's see, I would add the 4, it would be 4 minus 2xy over x squared when I solve for dy dx. And now if I do the derivative of the whole thing, that's why these two d's together will make that d squared y, and then over dx squared. So that's where that notation is coming from too. That d squared y over dx squared. Because you're doing the second derivative both times with respect to x of that function y, whatever y is. Okay, so now if I do the derivative of the right-hand side here, I'm going to have to use a quotient rule. So low d high. So low would be x squared times the derivative of the high, which would be 0, negative 2, y plus x y prime. So low d high minus high d low all over low squared. All right, so here's the thing, right? We're really, really close. But this is not in terms of x and y. That's in terms of the derivative. However, this is why this step is also important as well. This is in terms of x and y, and that is the derivative. Oh, look at that. So, what we expect you guys to do is to make that substitution. Your book is going to simplify a lot further, and I do not care about that. So y plus x times 4 minus 2xy over x squared. You guys will see in the homework, sorry, I'm counting my parentheses. You'll see in the homework, especially when you're looking at my work, how simplified I expect you to be. And it is really not that simplified at all. The problems like this that you see on the AP test or something, right? Now we are all in terms of x and y, right? Everything in there is x and y. There's no longer derivatives. If I look all over, those are all just in terms of x and y. So that would be my second derivative. But the questions like this that you're going to get on the AP test are not going to be so crazy. It'll be pretty straightforward as to how you simplify it. They're not trying to see if you can simplify. They're trying to see if you can do the calculus. That is their main goal, at least. So let's see. Here, same idea, right? Doing the derivative first. So that first part is a product rule. So I have y plus xy prime. Minus 1 would be 0, so equals 2 plus 2y y prime. So I'm going to solve for y prime first. So I'm going to make this y minus 2 equals 2y y prime minus x y prime. So I'm going to say y prime is y minus 2 over 2y minus x. Yes. All right, so now I'm going to do the derivative of that to do my second derivative. Move my work up here. So low d high get out of here. Low d high minus high d low all over low squared. All right, so the only things we need to substitute, and I can't highlight that, are these two things right here, right? This dy dx in both positions. So I need to substitute what I solved that for, which was y minus 2 over 2y minus x. All right, and there is some simplification there that you can do if you want to, but you don't have to. So you would say d squared y equals over dx squared equals all this junk, and that would be plenty for a free response type question. All right, I'm going to take a break and take a drink of water. All right, folks. So next topic we're going to get into is just essentially a different way of taking a derivative. It's just another option. There's lots of different ways that we have taken derivatives up to this point. Like we've talked about, if you have sine of x over x minus 1 or something, and say that's our function, you could also make this x minus 1 to the negative first times sine, right? So the first part, this would be a quotient rule, and this would be a product, right? We can also do something that would be a natural log differentiation. So this goes off the basic fact and the basic principle that, say I have something as simple as x equals 2. If I take the natural log, of both sides, this is still an equivalent statement. And I have not changed the value of x, and I have not changed the value 2, right? Still x would be equal to 2 in both cases, but I've just changed how the function looks. Something else we could do is I could say that this is 2 to the x equals 2 to the 2. This is called exponentiating, which really isn't that useful, but I'm just trying to show you that it's equivalent. So as long as I do the same thing to both sides of an equation, right, that's that basic Algebra 1 principle. If I do the same thing to both sides, then it still keeps it equivalent. So we're going to use this fact to make differentiation a little bit easier for us, right? So on this part A1, we can do this without doing what we're about to do. We can do it without doing a log for sure, right? It would be a chain rule with a product rule with a chain rule. And we've done problems like this up to this point. But let's write it using the logs and see kind of how it changes things for us a little bit. So if I take the log of both sides, and especially if we remember properties of logs, that's where the big thing's going to come in, right? So properties of logs, just to remind you guys, ln of a times b is the same thing as ln of a plus ln of b. Oh no. If I have ln of a divided by b, that's the same thing as ln of, that's not an ln, that's just ln of a minus ln of b. If I have ln of a to the b, right, where that exponent is on the a, this is the same thing as saying b ln, that's just law, ln of a. Right, so those are properties that you guys learned in pre-cal. These are properties of logs that are very important. You also have the change of base, but we're not going to use it that much in this stuff. So if I use my log rules here, well, this square root, I'm going to rewrite that as to the 1/2 power, because what that allows me to do is to move that 1/2 out front. Right? And then on the inside of that log now, I have a multiplication. So with that multiplication, I can make it addition. And then check it out. I have some exponents. I have a 3 there and a 3 there. That with this property up here, right, with that property right there, I can bring that 3 in front. So that 3 times that 1/2 would be 3/2. So really what I want to do is take the derivative of this stuff. So if I take the derivative with respect to x, right, this is what we've been doing up to this point with the implicit differentiation. I don't necessarily have to have the y by itself. On this left-hand side over here, I would have 1 over y times y prime equals 3/2 times 1 over x plus 3/2 times 1 over x minus 4. And that I have taken the derivative. That's That's it. That's all I needed to do to take that derivative. So it makes it a lot faster once you get really good at these properties of logs. So I'm going to take this, I'm going to move it up over here. So now that 1 over y on this left-hand side, I do need to move this. I need to get rid of this. And I need to multiply it to the other side such that I have the y prime by itself. So if I multiply it up to the other side, then I have y prime equals y times, what, 3 over 2x plus 3 over 2 times x minus 4. Well, what was y? Y was my original function. So I have y prime is the square root of x cubed times x minus 4 cubed times all of this junk on the inside. So 3 over 2x plus 3 over 2 times x minus 4. And that is it. That would be my derivative. So again, you could get to the same position if you guys do the derivative the normal way. And some of you will be faster at this at first, but I promise there's going to be ones, especially on BC, especially if you go into BC, you are going to need to do this because you don't know how to take the derivative otherwise. And we'll see one here in just a minute too. But it definitely makes finding the derivative faster for some of these. So like this one probably isn't that horrible if I don't use the log rules. But let's see. ln of y equals ln of, I'm going to go ahead and rewrite the exponent. So I bring in front that 1/2. So I'm just going to rewrite this. So ln y equals 1/2 ln of x squared plus 1. The division turns into subtraction. And notice in both of these problems, I didn't really talk about it, I didn't think about it, but the 1/2, if you split up the logs with addition or subtraction, you need to bring that 1/2 with your log. It's still applying to that log. If you get rid of the log, then you are saying it no longer applies, but that is not the case. Okay, and now I'm at the point that I can take the derivative. So I'm going to take d over dx, and I will have 1 over y times y prime equals 1 over 2, 1 over x squared plus 1 times 2x minus 1 over 2, 1 over x squared minus 1 times 2x, right? And all of this is using the chain rule with these natural logs, right? ln is 1 over the thing inside times the derivative of the thing inside for both of those logs, right? This one and this one right there. Okay, so then multiply that y and rewrite y for what it is. So y prime is square root x squared plus 1 over x squared minus 1 times all this stuff inside. Oh, that was a bad parentheses. Must have erased it. 2x over 2 times x squared plus 1 minus 2x over 2 times x squared minus 1. Again, I know there's a lot more simplification that could be done. It does not have to be done though, so I'm going to leave it like that. Alright, so last one. I think this is the last one for the entire notes. This is one that you would need to do logarithmic differentiation on. There's no other way to do it. And really, it's pretty simple, and these are the ones that, to me, it's the most useful for. So if I rewrite this, and I take the natural log of both sides, so ln y equals ln of x to the 3x. The nice thing about my power property for natural logs and logs is that I can move that 3x out front. So I have ln of y equals 3x ln of x. So no longer does this become a derivative x to the x that I have no idea what it is. It becomes something that I can use the product rule for. So if I take the derivative using my implicit differentiation, I can have 1 over y times y prime equals, so the derivative of the first, I'm going to make this u and v, u, v. So I'm going to do u ln of x plus 3x times 1 over x. So this becomes y prime is y, which was x to the 3x, times 3 ln of x plus 3. And that's it. That would be my answer. You can probably generalize a rule for these things, but I don't know. Natural log makes it pretty easy for us to be able to take the derivative of these things. Okay, other than that, you guys have homework on these questions. So as you are looking at the things, let me know what questions I can answer for you guys. And go have some fun. And I'll talk to you guys soon.